First of all, I would like to express my thanks to Professor Ali Gencer and the organizers for inviting me to this beautiful conference. And in this talk, I will present some recent results on superconductor nanoarchitectures, which were obtained mainly at Leibniz Institute for Solid State and Materials Research in Dresden. It's a collaborative work with Roman Rezaev, Kate Smirnova, and Oliver Schmidt. Here is an outline of my talk. It's a graphical outline. I simply indicate which structures will be discussed in next time. It's open micro and nanotubes. It's C-shaped nanoarchitectures and nanohelices. All these structures have been recently overviewed in my book this year, self-rolled micro and nano architectures, and the range of phenomena is much wider than superconductivity, but within this conference I will confine myself to superconducting nano architectures. And the motivation for our work comes from experiment. There have been tremendous advancements in possibilities of fabrication, characterization, and application of samples at micro and sub-micro scale with curvature. Because this is the first presentation of our cycle at this set of conferences, I will take 1 minute in order to show you which technology underlies the real physics of this phenomenon. Imagine a double layer of two crystalline materials which are super thin, maybe 100 nanometers. And they are put on a substrate, but not directly. There is another third layer, which is white. Oh, you can see this white layer. And this is sacrificial layer. Why is it sacrificial? If you start etching it off from the side, two layers which contact each other occur in strained state. Different crystal lattices try to adjust themselves to each other. But this leads to the occurrence of strain. And this strain can be released by deformations. Deformations can be different, but under certain conditions which were revealed in this group of Viktor Yakovlevich Prince, who unfortunately left us a few months ago, and Oliver Schmidt actively developed this field. The deformation is rolling up, as you can see. And then everything depends on the duration of the process. It can be half roll, it can be one tube, it can be more, it can be radial superlattice. Today I will speak about single nanotubes. What is important? That this is not a whole cylinder. Due to this process, after rolling up even over 360 degrees, you arrive at different positions, so you have two edges of this cylinder. Therefore, it's called open cylinder or open tube. Next to this fabrication method, I would like to mention here also extremely powerful methods which have been very actively developed and exploited recently is focused electron beam induced deposition and focused ion beam induced deposition, which allow to produce nanoarchitectures at sub-micron size. I must rush because time is limited. This is our first idea. In the course of my presentation, I will show how this theoretical first idea was developed towards real experiment. But the initial idea is, if you put contacts to these banks of the slit, and if you let transport current flow azimutally over the cylindrical surface of this cylinder, then in case, if there is a magnetic field orthogonal to the axis, two groups of screening currents develop. No Meissner current in big system. And here you will have one set of screening currents in the upper half cylinder and another set of Meissner currents in the lower half cylinder. Instead of one pass along the perimeter of the membrane, which you recall from textbooks on superconductivity. Topologically, it's already a new situation. You have two loops, disconnected loops, which have different topological properties as respect to one loop. And this leads to all the phenomena which I will show now, but what is extremely important circumstance here, that the normal component of the magnetic field, which itself is uniform, but the normal component is strongly modulated along the azimuthal angle. So here it's maximum, here it's minimum, but on the sides of the tube it's zero. The magnetic field is inhomogeneous, and this inhomogeneity is controlled, and its size is 1 micron or lower. It's a great challenge for experiment to generate such a magnetic field if it's done different ways. Our approach to analyze the state of superconductivity is based on time-dependent Ginzburg-Landau with its appropriate boundary condition, on Poisson equation for scalar potential, which gives you the potential, and Maxwell equation for possible renormalization of the vector potential. Our approach is based on finite difference time domain approximation with link variables which allow us to obey gauge invariance, very important in such structures, but I will skip the slides. If somebody of you is interested, please turn to me, okay? And the results are shown here. What happens in such a tube? First of all, without transport current. If magnetic flux is set on, there is one vortex on average in the upper half and one vortex in the lower half. If this flux is higher, then we have a chain of vortices. If magnetic flux is still higher, we can have two chains of vortices, for example. And if you then turn on the transport current, which I repeat flows in the azimuthal direction, then the Magnus force pushes these vortices in the upper part in one direction, for example, to us, but the vortices in the lower half in the opposite direction, because the direction of transport current is opposite in the upper and lower half cylinder. At this point, please take into account that this is not a full cylinder, and this is not an abricosal vortex in that beautiful sense which we recalled yesterday. This is a very narrow tube, and these objects are vortices, but they are very, very narrow. They are slices of abricos of vortices, and they are so far from each other that they do not feel each other inductively. They may move in opposite directions. Okay, these are typical times which occur here. You see, this is time between two consecutive instances of nucleation of a vortex at a certain place. And this is the time of flight, if you like. How long does it take for one vortex to reach another edge of the tube in order to denucleate? These times are lower than 1 nanosecond. You can immediately calculate the frequency, which we get here. It's 10 to the power 10 hertz, and what is it? It's the generator of frequency. It's a clock or an eventual systems of fluxonic handling of quantum information. If you like quantum computing, but there are also other systems for this. So this is the first what we observed. And I must be faster now, yes. Please look at the insert in this panel. It shows these two times which I have just mentioned, a time between two nucleations and time of flight. And when they cross, we have just one vortex at a certain time. And if we compare planar structure and rolled up nanotube made of the same membrane, we see that this characteristic magnetic field, which indicates the transition between sparse to dense vortices, increases by a factor of 3. So, by rolling up, we change physical properties of materials. Though it's the same material, it's the same membrane, but it's enough to roll it up, and we get another parameters which can be measured. I think this is one message which you can think of. And I will go further faster. If we increase a magnetic field, then between single vortex and two vortex regime, there should be something in between. Something occurs dynamically. It's bifurcation. Just between these regimes, look at its magnetic field between. A part of chain then splits in two, and these two have two different typical times, and I have already a generator of two frequencies in one tube, so it's a clock with two different tempos. Good. We have approached now the key message of my presentation, and I hope to be on time. Okay. All what I have presented refers to the case when the current is not too strong. But if we increase it and if it approaches the critical current, then this transition between vortices in one chain and vortices in two chains occurs via a very unusual stage, which is shown here. On the amplitude of the order parameter, you see a suppression. But if you look at the phase diagram, it's a phase portrait of the distribution, you see vortices and anti-vortices, which generate with extremely high speed, and then they move under the same Magnus force, but they move in opposite directions and annihilate these neighboring anti-vortices or vortices. And here the lifetime is 3 orders of magnitude smaller than for chains, but they move so fast that the resulting induced voltage is peaked here, and this peak is 3 times higher for niobium and 5 times higher for tin than in the case of chains. So we can influence the induced voltage which gives rise to resistance. Resistance can be measured, or quantities which are related.
5 minutes.
Yeah, thank you. Okay. During these 5 minutes, I would like simply to give you a flavor of our ongoing investigations. So this is an investigation of how this transition from chains of vortices to phase slips, which are associated to the suppression of the water parameter, though there are vortices and anti-vortices. This is another type of topological defects. And it occurs that this transition is very rich, and it depends on the way how you switch on the transport current or magnetic field. The previous results suppose that the transport current is switched on instantaneously. But now we know that if you give it abruptly with the time of switching on of the order of 10 picoseconds, it's really in a very fast peak in the voltage. Estimate here the height of this peak. This is a few times. It's an effect which is really prominent. But if you make this switch gradual, say 1 or 2 orders of magnitude more gradually, you will have a very smooth transition between these regimes, because the system can adjust its ground state smoothly to the current or to the magnetic field as shown here. And as a natural consequence of this, if you change, for example, transport current in one direction and then decrease it in another direction, you might have a hysteresis of the same voltage generated or resistance, if you like. And this is because the stable state and the metastable state, if magnetic field is big enough, larger than 5 millitesla, they are strong enough so this in a certain interval of currents this difference of states is clear. This is our publication, which has put on archive today at midnight. And very last, but certainly also very recent work, Professor Dobrovolsky, who is here, we can add also an AC current to our DC current, and it's a transport current which is modulated in time. And this is really a cornucopia of different topological defects. I have no possibility to go into details, but there are changes between individual vortices, vortex chains, phase slips, and even phase slips develop in the direction orthogonal to the paraxial direction. There are different sorts of phase slips, and all this develops in time. If you then plot the dependence of the induced voltage on time, all what I have shown is only one period. It's maybe about one or two nanoseconds, and certainly the Fourier spectrum of these dependencies strongly depends on interplay between the frequency of accumulating current and the frequencies which are related to the intrinsic processes which I started with from the very beginning. I think at this moment I would like to tell you that curved superconductor architectures open really new possibilities to control the materials parameters and phenomena related to topological defects. This is in collaboration with Alexander Dobrovolsky, Igor Bogush, Rosa Cordoba, Jose Maria de Teresa, Herman Suderov, and Francesco Tafuri. I thank you for your attention.
So you mentioned that the vortices in the two parts of the cylinder, the open cylinder, would move into different directions, right? I wonder if you could measure also this, or is a theoretical prediction, because it may be possible to measure this effect, right?
In fact, the experimental relevance of this theory will be demonstrated in my talk after the talk by Professor Rudnin. But in short, they do not move from upper part to lower part. They nucleate, move, and denucleate. And others nucleate, move, and denucleate after having traversed the tube in different direction. It is not possible absolutely to look this motion of a vortex from upper to lower part because there are no vortices, they do not exist.
Thank you very much for very good presentation. I wonder, you say that in your presentation these can be used as a frequency source, and also it can be used doubled or tripled frequency source.
Absolutely.
At different frequencies.
At different.
I wonder what is the obstacle to reach very high or limit of the frequency. For example, what about the highest frequency, or what is the obstacle to reach higher than limit?
Okay, this is very nice question. We see the immediate possible applications. For example, from a peak, you can go to the idea of a sensor. You will sense the field. But from the frequency, you must control the time of flight. So if you make this tube shorter and shorter, the time of flight will be smaller and smaller, and the frequency will be higher. This is my qualitative answer. We can influence those frequencies within a wide range by manipulating the sizes, and also otherwise by changing the geometry. But again, I would refer to my next presentation.
Okay. One more question. I wonder, do you say that two different crystalline to different layer, right? And also you applied the voltage. So you mean there is a different direction current, so effect to each other, and then roll the upper side, right? So is there any electrical insulator between two layers, right? So
there is no current during the rolling up. It's thermodynamics, because there is a freestanding bilayer. There develop a strain, and they turn not due to any current. They roll up due to the strain.
Okay.
Yes, please.
Could you tell me, please, what is the expected current, what is the expected coherence length for these structures? Superconducting coherence.
No, but by the order of magnitude, in niobium, it's, I think, of the 100 of nanometers. With other materials, we can also vary this quantity significantly, and I think in case if you arrive at a very dense vortex stage, this intrinsic properties of superconductor will be also changed. But what I told, this is a typical size like in 3D.
Yes. Thank you. All questions and comments.